chapter 3 seems like we should be further than chapter 3. I feel like we've done a lot of stuff this year to only be on chapter 3. But in math class, we go pretty slow. We do a lot of stuff in one chapter. But chapter 3 is exponential, logistic, and logarithmic functions, which means, again, most of this should be reviewed from Algebra 2, talking about exponential function, exponential growth, exponential decay, talking about logarithmic functions, like the logs. Remember all that log stuff you did last year? And all the applications with it, all the half-life stuff, lots of sciencey applications that we can talk about the half-life and how old something is. There's lots of finance stuff that we can talk about, finding interest rates and a whole bunch of stuff. Anytime you get a loan out, there's an exponential function involved. You don't actually do the work because they type it all in for you, but it really is using math. And so there's a lot of applications for this. We're going to spend today talking about what exponential functions are, what their graphs look like, and talk about that number e, which hopefully won't be too bad. Oh, wait! I think I finished your notes.
Oh, that's fine.
Wait, what if I did it? What if I'm lying to you?
I labeled it.
I think you did.
Thought I did. I don't see my data. What if I find it later and then I won't tell you so that you don't remember. Maybe I just remember printing them for Megan. Did I print them for Megan?
They're going to say 6 hours.
I only printed for 6 hours. That's not true. My life is a disaster, so then. It looks super great as I'm recording right now. I told him he should come and sub again.
He's a preacher. He can't
Hey, Grady, you better be watching this.
He's not going to.
I know.
So we can talk about this. Let's move on. All right. Exponential functions. This is kind of a nice little vocab word. Something to know. Transcendental functions are functions that don't have very nice solutions, right? Numbers that are not the solution of a polynomial equation with integer coefficients. Because with exponential and logarithmic things, remember we get a lot of irrational, weird answers there. We're going to talk a lot about exponential growth and exponential decay, but today we're just going to talk about that an exponential function right here, like y equals a times b to the x power. It's an exponential function because there's an x in the exponent. Makes the shape completely different. They give you lots of rules here about the letters. A is non-zero, because if A was 0, then the whole thing would be 0. B is positive, and we'll talk about, yes, sometimes it can be negative, but in this case, we're talking about B is positive. B is not equal to 1, because anything, like 1 to anything is still 1, so that doesn't change anything. And X can be any real number. We call A the initial value, and B is the base. And when we start talking about writing equations, the initial value is like where you start. If you're talking about chemistry stuff, if you're talking about half-life stuff, it's like how much was present initially. If you're talking about population, it's like the initial population is what your A value is. It's where you start. And B is the base, whether it's growing or getting smaller. If it's growing, then B is always a positive number. If your population is decreasing, right, then B might be a number less than 1. So part of your homework today and part of your next test is very exciting. I just want to know that you can use a calculator. And so these first couple problems, after all this stuff that you didn't have to write, thank goodness, right? It just says evaluate each function to the nearest thousandth because we are approximating some of these values. You're just going to plug in that number and you're just going to use your calculator. And you might think that's silly, but as we start doing some of these story problems, you have to use your calculator a lot. And it's important that you can use it correctly. So if you don't have a calculator, I'll give you one. Maybe I'll throw one at you.
That's not silly. No, we should have tested it.
Ready?
Oh.
Do you need one?
This is
Maybe
senior
just
stuff.
stealing it. It was an ECA lab a lot, and some kids asked for a calculator just so I threw it at them. It says to the nearest thousandths, which means you can just use your calculator, and yes, you can just use decimals. How many decimal places is the nearest thousandths?
3.
Tenths, hundredths, thousandths, which means round to the third decimal. Whether you round up or not depends on the fourth decimal, whether it's 5 or higher. So just make sure that you round correctly, because I will take a half point off if you round incorrectly. 3 to the negative 2 is really just 1/9, which is 0.111, I think. Now, this is 3 to the negative x, and there's a couple ways you can do this. I think you can just use the fraction button and 4/9. But if you don't use the fraction button, if you actually use the division sign, make sure when you use that power, which on my calculator is a caret, that you do -4 divided by 9. Because if you use the division button and you don't put that in parentheses, it will just take it to the -4 power and then divide the whole thing by 9. So you just want to make sure that you do that correctly. -4/9. I got 0.614. Did you get 0.614? And so when I do these on the calculator, a lot of times people just like to not actually try it. But I always say try it to make sure you're using the calculator correctly. Because during a test, I won't help you use your calculator. But up until then, I will help you type things in your calculator correctly. We also like to be able to write equations. We've written linear equations, we've written quadratic equations, and now they're going to give you some points and they want you to write an exponential function. And again, there's more than one way to do this. Sometimes you can just kind of see, like you'll just know what the base is because you can kind of see what's happening. But sometimes it's like a weird fraction, and you need to be able to take the formula y equals a times b to the x. And just like slope-intercept form, you have to find m and you have to find b. Quadratics, you have to find the vertex, which is h and k, and you have to find a. In this one, we need to figure out what a and b are using what they give you. And I think on the homework today, there's one that they give you this in an xy chart. So instead of giving you ordered pairs, they write it like this. So they say, well, like x is -2, y is 108, -1, 36. But it's the same idea. Or they could actually give you a graph with a couple points on it and ask you to write the equation. I like these types of questions because it really makes you think, do you know the formula and do you know what to plug in? We have 2 unknown values, so it's really kind of important that they give us what it is when x is 0. And I'll plug it in this time, and then maybe we can see a shortcut with this. But if they tell us what the y value is when x is 0, think what happens if we plug this in for x and for y. I get that 12 equals a times b to the 0. And what is any number to the 0 power? 1. So I just get that a is 12. You'll look back on the previous page. I told you that a is always your initial value. Your initial value is what it is when x is 0. And so if you recognize that, you don't have to do this work every time. Like you'll just say, oh, x is 0, so that must mean a equals 12. Or just do this every time. Pick that point first and plug it in. Yeah. So I can say I know it's y equals 12 times b to the x power. And b is the base, like what's happening to the problem as you go. And again, sometimes people are really good at seeing that. I'm very much an equation type person. So just like all the other stuff that we've done, linear and quadratic, to find b, I'm just going to pick another point and plug it in. And it really doesn't matter what point you pick. Right? You could pick any of these x or y's and plug it in, but which point do you think would be the easiest to plug into this problem? 1, 4, because if you plug 1 in for x, you just get b to the first power, so you don't have to do any work. You could pick any of them, but you just have to do an extra, like if you had b squared, you have to take the square root. Or if you had b to the -2, you'd have to think about how you would get rid of that. And so try to pick what's going to make it easier. So I'm going to say that 4 equals 12 times b to the first, or that's just b. So I'm just going to solve that, just like we solved for a in those quadratic functions, just like we solved for b in y equals mx plus b. And I get that my base is 1/3 on this problem. So write the equation, determine the formula for these points would be y equals 12 times 1/3 to the x power. And you could check that that's true, but it really does work. A lot of times the base is going to be a fraction just because they don't want you to be able to maybe just see. They want you to do a little bit of work.
So they give you all those points, but technically you only need 2.
Yeah, you really only need 2. Which means I think there's one on the homework that they give you all the points, There's another on the homework that they just give you a graph with only 2 points, because that's really all you need is 2 points. So yeah, all those other points are really not needed. Questions about that? That's something that we'll review again, probably on your test. I'll give you a question like that because I like those questions, because they really make you kind of go through the process there. The next ones here, I put a few graphs here, mostly just because I wanted to remind you the shape of these, and think about the domain and the range of these as we do it. And so I'm just going to pick some values for x and y here just to remind you. Exponential functions, especially when your base is not a fraction, idea is it gets big pretty quickly, right? So usually the base is pretty small, because think about if it was 5 to the x, if you plug 2 in there, you're already at 25, so it kind of makes your graph really big. So I like 2, because if I pick 0 and 1 and 2, let's just go with that first. If I plug 0 in there, 2 to the 0 is 1. I plug 1 in there, 2 to the first is 2. I plug 2 in there, 2 squared is 4. And it's just going to keep growing as a power of 2, right? You plug 3 in there, you get 8. You plug 4 in there, you get 16. But what happens when I plug negative numbers in? 2 to the negative 1, what does that actually mean? Yeah, it just moves it to the bottom. So you're going to get 1/2. If you plug negative 2 in there, you're going to get 1/4. If you plug negative 100 in there, you're going to get 1/2 to the 100th, which is still not 0. And so I want you to be aware that these do have an asymptote. Way back in chapter P, when we talked about horizontal asymptotes for the first time, they gave you an exponential one, and you can't use the rules for horizontal asymptotes on this because you can't think about the degree of the numerator and the degree of the denominator. But exponential functions always have a horizontal asymptote, because there's going to be a point that it can't get to a certain value depending on the transformations here. But the shape is very much the same on all of these. This is a really, really small graph. But if I did 0, 1, 1, 2, 2, 4, right? This side's going to go up fairly quickly. This side is going to keep getting smaller, but it's never going to get to 0. There's no number you can plug in there for x that would ever make it get to 0. And that is the general shape for an exponential growth model, meaning as x gets bigger, y is growing exponentially at a very fast rate. If we talk about, in biology, we talk about bacteria multiplying at an exponential rate because they reproduce so rapidly, going up very quickly. And just to show you real quick that 3 is going to be the same shape, the only thing that happens is it's going to go up at an even faster rate, so I'm not going to pick a million points on this. I'm just going to pick negative 1, 0, and 1. When I plug 1 in there, 3 to the first is 3. When I plug 0 in there, anything to the 0 power is 1. And when I plug a negative in, it just moves it to the bottom. So I get 1/3. Think about if you plug 2 in there, it's going to go all the way up to 9. So if you really wanted to graph 2, 9, right, it goes up at even a faster rate. But again, that shouldn't go under here. This side is just going to have that horizontal asymptote. And then we also want to talk about transformation. So I just threw one in here. What if I threw in that the x was negative up there? And maybe you can remember about transformation, what's going to happen. But now if I pick negative 1, 0, and 1, if I put negative 1 in there, that's now 2 to the first, because negative of negative 1. So now that side's going to be the positive side. I plug 0 in there, I still get 1. And now if I plug positive 1 in there, I get 2 to the negative 1, which is 1/2. And so it's like it's flipped over the y-axis. So now this side's going up, and this side's going down. That's one way we could talk about an exponential decay model, because x is getting smaller over time, y is getting smaller over time. So on the next slide, I just have some like comparing these growth and decay models, domain and range. We could think about that before we write it down. The domain on these, can I pick whatever I want for x on these problems? Can x be a fraction? Can x be negative? Can x be positive? X can be anything. And if you look at this graph, think about it's going to include all negative x values and all positive x values are going to be used. So the domain on these are all real numbers, but the range is never all real numbers because it's always going to have like a stopping point that it doesn't get any lower. Obviously, we can move it up and down and change that, but on these, it's always the x-axis that it stops. So notice the two things I did here. A lot of these are going to be the same, but this is, if you have a number bigger than 1 and your exponent's positive, we're going to say that's a growth model, so it's going to kind of look like this. But if your number is bigger than 1, your base, but your exponent is negative, it's always going to flip it over, and we're going to say that's like a decay model. But you're going to see that both, like these are very similar answers here, even though it's growth and decay. The domain on both of these is all real numbers. Even with transformations, it's going to be all real numbers. But the range is going to be what is the lowest that it ever gets. And on these problems, if there's no vertical shift up or down, the range is never going to get to 0. So we're going to say from 0 to infinity, not including 0. There's no number for x that you could plug in there that will ever get you 0. That will ever get you a negative number. So I guess, how else do we write that? Y, such that y is greater than 0, if you prefer. And it's the same thing for this. I don't know if you just want to write it in the middle and say true for both. Also, if you notice those three graphs we did, the y-intercept was the same on all of them. Because when you plug 0 in for x, anything to the 0 power is going to be 1. Again, transformations could change that, but the parent graph, that's true. And notice I kind of filled this in for you. These are both continuous graphs. There's no asymptotes, like no vertical asymptotes. But this is an increasing graph. It's going up. This one is a decreasing graph. And your horizontal asymptote is always going to be wherever your range stops. So our horizontal asymptote on both of these would be y equals 0. And as we look at crazier ones, this is kind of a nice thing to go back and look at. And so just like every graph we've done in here, you can make an XY chart every time. But if you are aware of what the normal graph looks like, and you're aware of transformations, you don't have to make a million points to get the shape of the graph. And so on the next slide here, I kind of gave you a few graphs here. And again, I picked 2 to the x just because it's easy to graph a lot of points on 2 to the x. And I know you don't really have color-coded pens for the most part, but I thought we could graph 3 transformations here, or at least write out what the transformations are, to remind you that the same transformation rules that apply to quadratics, that apply to square root graphs, that apply to absolute value graphs, apply to exponential graphs. So, I don't know where my blue marker went. It's been missing in action. I need like this in my life to just be some losing things, but that's right. You know what I can do? I can just craft with. I make this one. Oh, look, there we go. Perfect. Who needs a book marker? I'm going to graph 2 to the x, just like we did already. At 0, it's at 1. At 1, it's at 2. At 2, it's at 4. At 3, it's at 8. And that's what I'm going to call my parent graph. So I don't know which one you want to do first. Maybe some that you realize more than others. We kind of struggle with the negatives sometimes. But if I put a negative 2 to the x, what's going to happen when I graph that problem? It's going to flip, and I'm going to get negative y value now. Negative y values, right? It's going to flip over, so you could think like, if you wanted to pick a point here, if you picked 1 for x, you're actually going to get negative 2 instead of positive 2. And so this is going to reflect in x-axis. If you forgot that, you can always just make the xy chart, and you'll get the same values. but I just like to remind you that this kind of speeds things up. So I can be like, oh, if I plug 1 in there, I'm now going to get -2. If I plug 2 in there, I'm going to get -4.
If you plug 0 in instead of 1.
So it's kind of tricky on this. It really should be -1 because think about I know it's kind of weird, but they're saying like you do 2 to the x and then you would do the negative. Does that make sense to what I'm saying? And so I'm with you on that because you kind of think it should still be 0, but they're doing like this. 2 to the 0 and then the negative in front. And so it is just going to flip straight over and be sort of like this. So just like those parent graphs that I taught you in chapter 2, those library of functions that I said you should know, exponential functions are always the shape, so we can just use the transformations. What about if something's added or subtracted up in the function? Do you remember what that means? Which way it moves?
Left.
Yeah, it moves left or right. That's a horizontal translation. So since it's positive, this actually is going to move left 1. If you forgot that or if you aren't sure, start with what makes that go to the 0 power. And instead of it being 0, right, if you made your XY chart, you'd have to pick -1. And -1 plus 1 is 0, and 2 to the 0 is 1. So it's kind of shifted back. It's going to be kind of hard to do this all in one, but at -1, it goes up to 0. So now if you plug 0 in there, then it goes up to 2. So again, some people say I don't need to learn the transformation rules because I can just make an XY chart, which I'm okay with. But it is going to still go up, it's just going to be kind of moved back a little bit and go down slower. Like, look, I didn't even label these. If you don't have different colors on your paper, my advice is that you label each one so that if you ever go back and look at this, it doesn't just look like a big giant mess on your paper. And the last one, 2 to the x plus 3. A number added or subtracted outside of the function is a vertical shift, which is really important because it's going to change our asymptote, right? This is now moving up 3 units. So again, if you made the XY chart, if you picked 0, that would be 2 to the 0 is 1, 1 plus 3 is 4. And if you know it just moved up, then the same shape's going to happen now. Like if you picked 1, now it's going to be 2 plus 3 is 5. But really, really important that you get the asymptote correctly, right? Don't make that come all the way down to 0 because it's not going to. And if you're not sure what the asymptote is, pick some of those negative numbers. But the asymptote will always be whatever's added or subtracted outside that function, because that's going to change your vertical or your horizontal shift there. I'm screwing that up. Your horizontal asymptote, which is the vertical shift. So I know that my asymptote is at 3. If you weren't sure, if you plugged -1 in there, you would get 1/2 plus 3, which is 3.5, and then you'll get 3 1/4, then you'll get 3 1/8, and it's going to get closer and closer to 3. So what I'm looking for when I'm grading these is that you don't cross that asymptote, right? If you make that line come all the way down, it tells me that you didn't know your asymptote changed. Questions about that? Maybe some vague memories of that? The other thing that's in this chapter or this section is E. E is a number, right? There's a button on your calculator, the E button on your calculator, and we can graph e to the x just like we can graph 2 to the x, and E is just this special number, and so I kind of gave you some information about that. What? E is irrational just like pi. It just doesn't get as much attention as pi because you learn about pi all the way back in at least middle school because you talk about area of a circle and circumference of a circle, so they have to teach you about pi. But E doesn't really come up very often until algebra 2 because E has to do with the natural logarithm, and you don't really do logarithms until you get to algebra 2. But it is an irrational number. There's lots of applications. with population stuff and interest stuff. But if you find the button on your calculator, the E button, usually when you type E, it automatically gives you like an exponent because it wants to know what power you want to take it to. But if you just type in E to the first power, you get this number. And someone asked me once where E comes from, because pi comes from taking a circle's circumference divided by diameter. That's where 3.14159 comes from. Where does this irrational come from? It comes from adding up all these numbers, adding up 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. You know what those factorials mean? Like what that means? Not really excited to. 6 factorial means like 6 times 5 times 4 times 3 times 2 times 1. So instead of writing all that out, we say 6 factorial. So if you keep adding these numbers forever, you might say, how can you add numbers forever? But you can. That's where the decimals keep coming up. These get smaller and smaller numbers, which is why it just changes the end decimal here. And it goes on forever because this goes on forever. And so that's where E comes from. Euler looks like Euler. He's the one credited with E. I don't know why he called it E. I like to say because his last name started with E, but I don't really know. But that's where this comes from. You're never going to have to know that, but just in case you were curious. But what you need to know is this. The function e to the x is a special exponential function because e is a special number. And if you remember anything about logarithms and ln comes from the inverse of this function. And so that's why e is so important to us. Today, some of your homework, you just get to practice using the e button on your calculator. If you were going to graph e to the x, it's just going to be decimals, right? So it's not as pretty as graphing 2 to the x, but you can just use your calculator and take e to the first, e to the second, and it's still going to be that shape with a y-intercept of 1 and a horizontal asymptote like that. So don't freak out if they give you one to graph like this. So look at this. This is really easy, right? It's your favorite stuff, Maddie. A whole test of this. Where you just have to plug the value in. And so again, later on in this chapter, we're going to do a lot of applications where you have to enter a lot of more stuff. And so it's just me making sure you know how to find that button on your calculator. On my calculator, ln is the third button down, and e is second that. So you have to hit second ln. And again, it automatically gives you e caret, and you just have to put in the power. If you wanted e to the first, you have to hit 1 there. But we want e to the second. To the 1000th place is a good place to go. Right, that's not so bad. Look, I have some little flicker ones, but let's just do them and not flicker it. So how about do the negative one? Do e to the negative 3 and see if you get one of those answers. That's almost done. We never would have made it if I didn't do that right. Again, if you were going to enter a fraction on this, make sure you either use a fraction button or you use parentheses. Negative 3, think about is moving it to the bottom, so it makes sense that this should be a small number. And make sure you round correctly. Should it be A or should it be B? Right, that's what I got. So if we're rounding to 3 decimal places, this 7 tells me I have to round this up. It's a 9, which means A would be the right answer. There's lots of rounding issues, which is why I like to address it, because people get really mad when I take a half point off when they don't round correctly. So, and then what about this one? I didn't actually make us graph it, but I said describe how to transform this graph, e to the x, into this graph, negative e to the negative x plus 2. And again, multiple choice, little test taking strategies here. When I see the plus 2 on the outside, I automatically can eliminate some choices, because what does plus 2 on the outside mean is happening to my graph? It goes up 2. So right away, I'm going to say it's not A and it's not C. So what do you think? Did one thing happen or did 2 things happen with these negatives? The negative of a negative. D would be the right answer, which means it can look kind of weird because it's going to reflect in both axes, and then and move up 2. So definitely some graphing on your homework. Make an XY chart if you need to, and we'll talk about tomorrow, and then some just plugging in values with your calculator. If you don't have a calculator, definitely not a bad $10 to $12 investment to get one. But also, if you have a smartphone, you have a calculator, you actually have a sign. Like my phone, if I turn it sideways, I get lots more buttons, and so there's an E button, there's a LN button, there's a log button. If you have a computer or a laptop, if you just Google free calculator, you can get one online. You also have a calculator built into your computer or laptop under accessories. So you have access to calculators if you have a smartphone or a computer, or you can just do as much as you can and then come in and grab a calculator and finish it. But you definitely will be using a calculator a lot. So if you have one that you haven't been bringing or you want to dig one up at home, not a bad idea to invest in one of these. Notice I gave you some odd ones. Feel free to check them. 15 through 30 multiples of 3 and 39. I will make assignment sheets for you